Hi, it's Romeo Bruni, and today we're going to talk about gamma ray bursts. Gamma rays, as you are aware, are electromagnetic radiation. The electromagnetic spectrum of radiation spans from very low energy radio waves through microwaves, through the visual spectrum, into the X-ray spectrum, and the most highest of the energy waves are the gamma waves. Super high energy gamma waves. Obviously, they're produced by the most energetic processes in the universe. If you were to do a map of the night sky in gamma rays, you would see something like that. That across here is the Milky Way. We're seeing down here a blazar, which we'll talk about soon, and over in this area we're seeing three different pulsars. But you can see there's a continuous emission of gamma rays in the universe, and we can see a lot from the plane of our Milky Way. In this regard, in this case, the gamma rays being emitted are from energetic things like stuff falling into the accretion disks, into black holes like X-ray binaries, that kind of thing. Gamma ray bursts are something quite different. Gamma ray bursts are sudden, intense flare-ups of gamma rays that over a period of anywhere from under 2 seconds to a minute or two come in a huge quantity and then stop. And so they're very sudden and very extreme. Gamma ray bursts, unlike gamma rays from the typical spots of transmission, you'll see are spread out. If this is the whole sky and the Milky Way is across there, you can see it's what we call isotropic, meaning they're coming from everywhere, and they're coming from everywhere outside our galaxy. Gamma ray bursts are extremely rare. There's only 1 or 2 or 3 per galaxy per million years. So there's very few of them. We see on average 1 a day coming to the Earth because when they do occur, they are so bright, they blast their information across the universe. So we're going to be able to see them. There's billions of galaxies in the sky, and if only 1 or 2 per year go into a gamma ray burst, that's still enough because there's so many billions of galaxies that we see on average 1 per day. So they're very sudden and shocking amount of gamma rays are emitted in a very short period of time. How do we notice them? Well, first of all, gamma rays we would not notice here on the Earth because luckily our atmosphere blocks them out. The ozone in our atmosphere blocks gamma rays, and we don't see gamma rays. That's why to see gamma rays you need to go to space. In fact, the original gamma ray observations were by the Vela satellites, which the Americans launched in the 60s to monitor the Russians to make sure they weren't cheating on the nuclear proliferation treaty. So they launched satellites to search for gamma rays because nuclear bombs release gamma rays. Instead, they started to see gamma rays being emitted from the sky and not from the Earth. Gamma ray detection is quite difficult. Gamma rays are so powerful that ordinary CCDs aren't going to pick them up. They're going to blow them up. And instead you have boxes in space where the gamma ray comes through. It actually will hit some aluminum foil type thing, which will then interact through various forces and create a positron and an electron. And the positron and an electron are actually what are observed. So when we observe these explosions in space, you're actually detecting individual gamma rays that come through, and they actually count the gamma rays. So where do these gamma ray bursts come from, and how powerful are they? Well, they've sorted out by examining thousands and thousands of them over the years now that there's 2 types of gamma ray bursts, a long and a short. The short are under 2 seconds. The long, obviously, over 2 seconds and can last up to a minute or 2. It's been more or less clearly determined now that the long gamma ray bursts are from a phenomena we call a hypernova or a collapsar. And what happens there is that you have a giant star, and we're not talking your ordinary star, but we're talking giant stars that are approximately 30 to 40 solar masses, so very big stars, which are quite rare in the universe. These are called Wolf-Rayet stars. Wolf-Rayet stars are greater than 40 solar masses. Wolf-Rayet stars are very evolved large stars. So not only are they large, but they're near the end of their lifespan. And so they've stopped fusing hydrogen to helium. And in fact, like most stars that are about to undergo core collapse supernova, they've developed this onion ring kind of formation where the heaviest element, the carbon, is starting to form at the base. And outside that, you have the various other elements. The oxygen and nitrogen would be outside of that, and so on. As illustrated by this illustration here, we have the Wolf-Rayet star with the hydrogen at its very outer edge, or very little hydrogen actually, then helium, then the carbon and oxygen, and so on. And so to the very center, of course, it's the iron core that is at the very center. So you have a very large star, and when it goes supernova, when it develops an iron core, and iron is the most stable of elements, is no longer a fuel. So suddenly a star will run out of fuel, and a massive star like a Wolf-Rayet star will suddenly collapse, like all core collapse stars, but even more sudden, and into a bigger black hole. And a black hole forms immediately at the center. The black hole forms an accretion disk immediately at the center, and two jets form, and the jets punch out through the atmosphere of the Wolf-Rayet star that's not even fully yet imploded yet, and bursts out these jets. And these jets are the gamma ray bursts. If we happen to be somewhere in the universe aligned with one of these jets, then you're going to see them even though they're incredibly far away. For example, gamma ray burst 221009A. Now, it sounds complicated, but it isn't. Gamma ray bursts are named depending on the day they arrive. So gamma ray burst 22 happened in 2022, and that's October 9th. So October 9th, 2022, that's just last month, there was the brightest of all time. There was an explosion in space that released 10 to the 55th ergs of energy in only 30 seconds. For comparison, our sun emits 10 to the 51st ergs of energy in its whole lifespan. So this explosion released 10,000 times the amount of energy in 30 seconds that our sun will release in its whole lifespan. And this energy, obviously it's not spherically sent out, because if it was, there's no supernova that big, but because the jets happen to be oriented towards us, then we saw it. Just to go back to what I was pointing out before, the blazar. A blazar, and you see blazar 3C54, 453C there, that blazar, that is a continuous source of gamma ray. And what blazars are essentially quasars, and a quasar is a supermassive black hole with an accretion disk. And when you have an accretion disk and they get highly magnetized, you get the jets pouring out. So it's this kind of formation, but on a continual basis, because in the center you have a supermassive black hole that's there all the time, and you have continuous amount of stuff being fed into it, and that creates these jets. And if we happen to align up with the jet, that's called a blazar. That's not a gamma ray burst, that's a continuous gamma ray emission called a blazar. Notice in Wolf-Rayet stars, it's very important, is the rotation. These if the star is rotating rapidly to start, and the black hole and the accretion disk maintain this rotation. And of course you have these strong magnetic fields that are involved in this jet formation. So all long gamma ray bursts are are from a hypernova or a collapsar. That's when a massive star then collapses. And they are the most common of the gamma ray bursts, and we see about one a day somewhere in the universe happening. Short gamma ray bursts are bursts that are under 2 seconds, and they're from a slightly different mechanism, well, actually quite a bit different mechanism. And they're also called a kilonova, and they're from a neutron star merger. So we could have two neutron stars rotating around each other, and then in their last moments of life, they will merge or smash together, and you will get an instantaneous formation of something similar to this. You could have a black hole at the center with an accretion disk and the jets. And here you'll have energy sent out in form of the gamma ray jets, which will last only under 2 seconds, but be an enormous amount of energy put out in less than 2 seconds. Two notable gamma ray bursts. Well, actually, I shouldn't say two notable. This is one gamma ray burst. This is gamma ray burst in 2017, August 17. So August 17, 2017. You notice I have it here, GW. That's gravity wave. Gravity wave 1708-17. In other words, this very same event on August 17, 2017, where two neutron stars merged, was detected by LIGO, the gravity wave telescope that we have, the laser beams pointing out in orthogonal directions, able to actually detect the stretching and contracting of space when gravity waves are generated. So this event caused gravity waves to be detected in the LIGO, and thus gravity wave 1708-17, and of course Fermi and other space telescopes also noticed it as a gamma ray burst 1708-17A. The A denotes it was the first one that day. Obviously, there was more than one that day, and that would have been B, etc. So long gamma ray burst, short gamma ray burst. Interestingly, just to summarize then, so we have long and short gamma ray bursts. We have the kind of same mechanism. We have a neutron stars merging, and they quickly form kind of an accretion disk and a black hole. Or we have a collapsar, a Wolf-Rayet star, coming up and forming this black hole with a sudden jet that pierces out. The jet sends material out, and the material hits material that's in the outside edges, in the envelope of the star. And when these jets of gamma rays hit that material, you get more gamma rays and X-rays and all kinds of stuff emitted for brief seconds of time. Short gamma ray bursts and long gamma ray bursts. Interestingly, gamma ray bursts are not something to fool around with, because they're extremely powerful. I'll get to that in a second. Here's another example of different gamma ray bursts. Plotted time versus actual number of photons they capture. And you can see that basically every gamma ray burst is different. And that's because every Wolf-Rayet star is different. Some weigh 40, some weigh 38, some weigh 42, some are more magnetized than others, some have more spin, etc. So when they go supernova, they're all going to be slightly different. Interestingly, a gamma ray burst was hypothesized to have caused one of the mass extinctions on the Earth. There have been about 5 or 6 mass extinctions on the Earth, and the one that occurred 450 billion years ago was called the Ordovician Silurian extinction, or the OS extinction. And what happens there is that there was a gamma ray burst. If a gamma ray burst occurs within 3,000 light years of the Earth, it would be bad news. A gamma ray burst occurred then, which hits the atmosphere. Gamma rays don't make it through the atmosphere, but if it's a big enough burst, it will destroy all the ozone in the atmosphere, for one. It will interact with nitrogen and oxygen in the atmosphere and create nitrous oxide and nitrous dioxide. Both of those are very bad things for the Earth. The nitrous oxide helps to wipe out any ozone that's remaining. The nitrous dioxide actually blocks visible light. So you get some gamma rays getting through because of the nitrous oxide interfering with the ozone. And the nitrous dioxide blocks visible light. And so after a gamma ray burst, you tend to get an ice age. And that's what happened. There was the gamma ray burst, which wiped out the ozone, which made a lot more ultraviolet rays being able to get through, and that combined with the nitrous dioxide blocking visible light, and that led to an ice age. So gamma ray bursts are not a good thing to get in the way of. Gamma ray burst, here's another one, gamma ray burst 08, 03, 19. So that would have been in 2008, March the 19th, 2008, there was a gamma ray burst which occurred 7.5 billion light years away, yet it was visible on the Earth from there. So from halfway across the universe, for approximately 60 seconds to the naked eye, you were able to see this gamma ray burst. It's the furthest object visible to the naked eye ever. What the time it flashed, it would have been 21,000 trillion times brighter than the sun. If it was where the sun was, it would have been 21 quadrillion times brighter than the sun. So gamma ray bursts are incredibly powerful. Here is a picture of the various extinctions, and when they occurred, we can see the Ordovician Silurian extinction occurred at around 450 million years ago. So gamma ray bursts, quite uncommon, quite rare, but when they occur, they send their light across the universe. So even though there's only one or two every million years per galaxy, we've never seen one from our galaxy. There are Wolf-Rayet stars in our galaxy, so there's possible we could get one, but we haven't seen one. But if you only have one per galaxy per million years, if you have billions and billions of galaxies, then you're going to start to add up. And since they shine their light across the universe, we're going to see them. So gamma ray bursts, we see them. They're important. Let's hope that we don't get one in our local vicinity soon. My name's Romeo Bruni. I hope you've enjoyed this. See you next time.